has posted WCSS was one number even when the cluster was 2 or 3. I don't think it would be right because it's a weighted cluster sum of squares. So I create two clusters or within the cluster sum of squares. So I create two clusters. So I mean even from a logical standpoint as well, output was coming as 1. So you mean to say I did not get your question. What was that output that was coming as 1, which kept decreasing as the number of clusters increases, right? So what was I mean, you were working with a different data set or something. So it must be possible weighted so that within the cluster, when I take the sum of squares, obviously if the cluster is changing, if 3 clusters are changing, obviously the cluster sum of squares should decrease, even though not significantly. Okay, you meant to say it's a sum of squares, right? So if it is sum of squares, it's a overall, right? Within the cluster, I am looking at the sum of squares. So, okay, let me run it again. If you look at this scenario, just take this. That is my within cluster sum of squares. So for each cluster, this is the within the cluster sum of squares. So I can print for each cluster within the cluster sum of squares, or if I am typically looking at the overall solution, I can directly consider the total sum of squares of across the clusters. So when I am looking at total sum of squares, depending on what are the number of clusters that I am going with, the within the cluster sum of squares keeps decreasing. But I am more interested in where the sum has where the sum of where the decrease has actually flattened, where the change in where the fall in the sum of squares has actually flattened. So for each cluster you can print the total sum of squares, because it is nothing but if I draw it graphically, right? Let's say I have some cluster. These are the various observations that are there as a part of this cluster. Let's say I have another cluster. I have a few observations as a part of this cluster. This will become the cluster center here. This will become the cluster center here. This is the within cluster sum of squares. So this is the within cluster sum of squares that you take for each of the cluster. And I can also find out the total sum of squares, right? This total plus this total will give me the total within cluster sum of squares. So what we are saying is the total within cluster sum of squares should be the least possible. So for whichever, I mean, least possible means as I keep increasing the total number of clusters, this number will keep on decreasing. So I want to do a kind of a trade-off. After a certain point, the decrease is not that significant. So if it is not that significant, we'll say that we will not, that is a kind of a trade-off point for us. Distance, okay, let me just look at your question in detail. Is the distance between the centroid and each member of that cluster. That is what I was mentioning here. Now we have two clusters, so we should have two WCSs. Yes, you can print both of them, right? For each cluster. So one is you are just printing, try to understand within each cluster what is the distance. But the second thing is to take a final decision as to how many clusters is a good solution for you. You will add up all the within cluster sum of squares. Okay, how the movement from different clusters happen. Suppose distance from centroid is high for one observation. Then we think of no. Let me tell you. I think I explained it last time also. The process is very straightforward process here, right? Initially, you have some random cluster centers. So randomly out of your all observations, 3 observations will be picked up. Then each observation based on the distance, let's say I have some 170 observations. Based on the distance, each observation will be pushed into one of the clusters. Right? Each observation will be pushed into one of the clusters. So based on the new memberships that have come out for each of the clusters, there would be a simple, the C1, which was the initial cluster center, it would be now updated. The new cluster center would be updated. So earlier the cluster center was only one observation. Randomly, let's say this was the 20th observation. This was the 50th observation and this was the 100th observation. These were randomly picked up. But after the first iteration, so some of the elements, obviously 20th element would be in C1, 50th element will be in 50th observation will be in C2 and 100th observation will be in C3. No doubt about it because their distances will be 0. But first observation, it may go to C1, C2, C3 depending on the distance. Second observation like that. Now all of them we are allotted to either C1 or C2 or C3. So now C1 contains some 40 observations, C2 contains some 70 observations, C3 contains some 50 observations. Now the average of every variable of C1, every variable of C2, every variable of C3, that would become the new cluster center. Right? Then I will again find out the distance between the first observation and the new cluster center. Second observation and the new cluster centers. Third observation and the new cluster centers. Now based on that, we will be knowing whether one is the first observation, is it still going into the same cluster which was used for computing the cluster center? Or is it going into the next cluster because the distance to the second cluster now for the first observation, the distance to the second, initially let's say it was a part of the first cluster. But now because of the change in the cluster centers, one might not be going into the cluster 1, probably one might be going into cluster 2 now. So what we are saying, there is a change in the cluster membership. Now what we say is we repeat these iterations either until a maximum number of iterations or there is no more change in the cluster membership of the various observations. So when there are two consecutive iterations where there is no change of even a single cluster membership, that is when we will stop the iteration process. Is this process clear? Great. So you can even come back to me offline also, not an issues, right? Some of these questions when you are trying to address, right? In case you find some time and probably you can either WhatsApp me or you can mail me as well. That should not be an issue, right? Sometimes you will practice them at different points in time. So even if you are working out at later points also, don't hesitate to call me or don't hesitate to mail me, or WhatsApp is a better. You can put a message on WhatsApp and probably we can fix up a time and then connect on Google Meet as well. Okay, so I'll get started. Any other questions from anyone? Okay, so we are continuing the clustering. This is an unsupervised learning algorithm, which we have already discussed. I'll quickly revise some of the things that we have done. Quick revision. So we said initially that clustering uses the concept of distance metrics, right? We discussed about different forms of distances: Euclidean, Manhattan, Minkowski, Hamming, and we have also got introduced to Haversine distance and cosine. So there are various other distance mechanisms that are there. I think our friend Paras has actually shared a big list of distances. Probably one of you can even take up one such kind of an exercise to understand what is the kind of difference that is coming out when I'm using different kinds of the distance measuring algorithms, right? That way you can very well get a practice into the various distance computation mechanisms as well. So one of you can take up probably 20 plus distances are mentioned. You can very well think of seeing probably is there any kind of difference in the clusters formation, or how big is the difference in the clusters formation by using the different distance mechanisms. So we discussed very important distance mechanisms: the Euclidean, Manhattan, Minkowski, and Hamming. Hamming comes in more and more handy only in case of string based textual data kind of thing. Then we started working out with the data. We wanted to try different clustering mechanisms with respect to our data. So in clustering, we do not do any kind of prediction. As we have discussed earlier, it is called an unsupervised learning algorithm. Our objective is to just, so there will be no target variable here. And unlike the prediction problems that we have taken up earlier, the classification or the regression problems, where there was a target variable and there were a set of feature variables, we were trying to use different algorithms to find the relationship between the target variable and the set of feature variables. Whereas here, we do not have a target variable. right? Though what do we do when there is no target variable? We try to identify the proximity of the samples, which means which two samples are very similar to each other, which samples are very much different from each other in terms of the various features that they are carrying. So which means here your work is completely with the features itself. You do not have a target variable here. So your focus is completely with the feature variable. Now, for example, in our problem, we had all countries, a list of all countries, where child mortality, the number of amount of exports, the health indicator, the imports, income, inflation, like this, there are various variables associated with each of the countries. Now, our objective is to see which countries are very, very similar, very, very close to each other, and which countries are very, very far away from each other. So, this is what was the typical exercise that we wanted to take up, so that we can bundle all the countries and we can treat all of them similarly. Or the other way of talking about is, if I have a solution for one country, or if I have a development plan for one country which is in that cluster, probably I can think of similar solution to the other countries which are a part of the same cluster. So that way, once I cluster things, it becomes more and more easy to think through the solution. Similarly, if I look at, let's say, the customer related transactions data. If I do a clustering and I'm able to identify a few people as a part of that cluster, a few customers as a part of one cluster, and if for suppose I have identified a couple of people in that cluster have committed fraud, right? First of all, without looking at whether they are fraudsters or not, I have simply listed out all the transactions that they have entered into. And based on that, I found that these 10 customers are very, very similar to each other in terms of the transactions that they have entered into. So I got a suspicion. I have clustered all 10 of them into one single group. Now I have found that within the group, on a sampling basis, I found that I took two of them and I saw that those two have really committed a fraud for the bank. So now my immediate solution is the remaining 8 people who are there as a part of this cluster, because their characteristics are very similar to the remaining 2 people, with the 2 people who are there in the cluster. So my bigger suspicion will come out that these 8 people also, to some extent, would have committed a fraud. So at least I will get the suspicion regarding that. So that is where probably by clustering, we are trying to see which observations are closer to each other, so that we can generalize their behavior separately from the elements or from the observations who are a part of some other cluster. So that is what is the business significance. Now that is the reason we want our cluster to be as good as possible. Now, as good as possible There are two ways of looking at it. So one is a statistical way. So wherein we can use within the cluster sum of squares, and probably where the within cluster sum of squares suddenly takes a kind of a flatness. So that could be the number of clusters that we can typically suggest. So let's say this is the within sum of squares, within the cluster sum of squares. When there are two clusters, this is the within cluster sum of squares. When there are three, this is the within cluster sum of squares. When there are four, when there are five, when there are six. But there is not much of a difference between 4, 5, 6 because the within cluster sum of squares has actually flattened off. And that is where I can say a 4-cluster solution is more appropriate for this. So this is a statistical way. There is another statistical approach which is typically called as your Silhouette width or Silhouette score. So this one, what is that we are saying? We are not only talking about the within cluster sum of squares, we are also talking about the between cluster sum of squares. So I would compare the between, so I would simply take between cluster sum of squares minus the within cluster sum of squares. So between the clusters, the sum of squares should be very, very large. And within the clusters, the sum of squares should be very, very low. So the difference between the two should be very, very high. And this is called as the Silhouette score. Normally, if I talk about, let's say, A is the between cluster sum of squares, B is the within cluster sum of squares, then typically when I talk about the Silhouette width, it is generally taken as A minus B divided by the maximum of A comma B. So the higher the Silhouette width score, that solution would be the better solution. So these are the two most commonly used statistical approaches to finalize on the number of clusters that we would like to have. Whereas the second approach is from a business significance perspective. What is that we are saying from a business significance perspective? Okay, I have formed 2 clusters or 3 clusters, right? So for each of the cluster, can I see any significant difference in the proportion of the frauds that they have committed? So frauds was not used to create the cluster. But once the cluster was created, we can look at some such kind of variables and see how each of these variables has fared for each of the clusters. So if we are observing that there is a clear-cut segregation across the clusters for this particular variable that we are injecting now, you will see that this cluster solution is a better solution compared to the other solution. So this is a second way, mostly a kind of, so there is some amount of subjectivity there because we are talking about the business significance and how much of difference is there between the various clusters with respect to one or more specific variable. So that is where you can come in both the business way as well as the individual way. Okay. I mean business or the statistical way. So you could see some of the basic operations that we have performed. I don't think anyone has any issues on that. So normally we are doing a kind of the first step is if there are any categorical variables, you can convert the categorical variables into dummy variables, right? Dummy variables are nothing but the variables which take values only 0 or 1. Each categorical variable, depending on the number of categories that it has, let's say if it has n categories altogether, n minus 1 categorical variables would be created, and each of those categorical variables would become the new columns of the data, right? So we have discussed about this dummy variable concept in our predictive problems when we talked about the machine learning algorithm. So here also you would create a categorical variable. You would create a categorical variable. You would create a kind of a dummy variable corresponding to each of the categorical variables. Then, once you have done that, then you can also do a kind of a non-linear transformation as well, right? To bring the data more or less onto a similar grounds. Sometimes people suggest doing this non-linear transformation, and in some cases people simply say that we can still ignore, right? There are two schools of thought. So here we have done the non-linear transformation, which is like Johansson transformation, which would try to bring the data more and more closer to a kind of a normal. And after that, we can perform the scaling on the data. Sometimes people directly perform the scaling without doing the Box-Cox or Johansson nonlinear transformation. Okay, so we have done the standard scalar. Then we directly went towards the k-means clustering. All right. So before we actually run the k-means clustering, we need to go for pairwise distances. So we can use different kinds of distance metrics here itself. You can very well see there are different kinds of distances that are applied in this function itself. Right, you can see different functions that are applied. Sorry. Oh, sorry. You could see I can apply any of these distances, right? So we have right now applied the Euclidean distance, but you can very well apply any of these distances to it, right? So pairwise, you can calculate the distances. Now they are all scaled. So you know that, so if there are 169, 167 observations, so the distances would be more like 167 by 167 kind of a matrix. So you can very well see which observations are close to each other and which are farther away from each other. Now that is where we can fit in k-means clustering once we have done the distances. As I have discussed, let us quickly read through. So it allows us to define the required number of clusters. So we have to specify how many clusters. We start by taking an arbitrary number of clusters, let's say 3, and we will be using the elbow method, which is the weighted, which is the within the cluster sum of squares, or we can very well use the Silhout score. So we can rank, so whatever is the algorithm, the k-means algorithm that we are working with, it will choose 3 random points as the centroid. We have discussed that. So it will compute the Euclidean distances from the centroid to all the other data points. The algorithm, after measuring the distances of all the data points from the centroid, associates each data point with a centroid based on its proximity. So the observation number 1, observation number 2, observation number 167, they all are pushed to one of the cluster or the other. To measure how good the 3 clusters are separated, so if I want complete separation, then rather than the within cluster sum of squares, I can also look at the between cluster sum of squares. And that's the reason we will typically get the Silhout score as a better mechanism. So otherwise, the elbow method is primarily only the within cluster sum of squares. So we will actually vary the number of clusters from 1 to the square root of the number of observations typically. We will calculate the within cluster sum of squares for each of the cluster. We add up all that within cluster sum of squares, which is what we typically call as the inertia in this language. The within cluster sum of squares added across the various clusters is otherwise called as inertia. Right? So it's a sum of the squared distances between each point and the centroid. And I can sum up all those points after that. So WCSS value is the largest when k equal to 1. Only one cluster is there. Obviously, all the elements will be a part of that cluster. So some of them may be very close to the centroid, some of them may be very far from that centroid, but they have to be a part of the same cluster because we have to give only a one cluster solution. And because of that reason, what you will typically find is the weighted the within the cluster WCSS, the within the cluster sum of squares will be the highest when there is one cluster and would be 0 when the number of clusters is equal to the number of observations. All right. Then we have talked about the Silhout score. So Silhout score has to be more, and the maximum value that you can think of for a Silhout score is +1. And that too, that +1 is possible if you look at the formula also. I said A minus B divided by the maximum of A comma B. So when A is 1 or when A is a kind of the highest possible value, any value between the sum of squares, but within the sum of squares should be 0. Right? Whatever is existing, it is the between sum of squares. But within the sum of squares is 0, which means all the elements within the cluster, they are one single point. Then only the within the sum of squares will be 0. So within the cluster sum of squares is 0. Between the cluster is very high, non-zero. That is when we say that we will get a perfect 1. Similarly, if the between the cluster sum of squares is 0 and the other one is whatever is the value, then that is when we can typically get the least possible value of fill out score, which could be -1. So that's where we can say that the range of the fill out score could be -1 to +1. -1 indicating that the within the cluster sum of squares is very high, whereas the between the cluster sum of squares is negligible almost. So which means they are very well separated. The clusters are very well separated because we are seeing between the clusters the distance is 0, whereas within the cluster the distance is very high. So the difference between these two would be much negative, right? And that is where we can say that the minimum most value of the Silhout score can come in, which is -1. All right. So this is one way you can very well measure the goodness of any clustering model. So what we could see, let's say initially I'm starting with just doing. Let's look at this code. Initially, I'm trying to create a k-means algorithm with one cluster. I want to do this 100 iterations. So within 100 iterations, if the clusters do not exchange, if every observation goes to the same cluster in 2 consecutive iterations, it would be stopped. Otherwise, after 100 iterations, this mechanism would typically stop. Right? So we are initially, this line will execute the clustering algorithm. Then what we are saying is, whatever the labels that come out of this algorithm, so like cluster 0, cluster 1, and so on, you create an extra column called clusters and assign them to that. So we are printing the clusters for each of the column. What is the cluster to which the data belongs to? So we are seeing that this is how the cluster, and we are also printing what is called as the within the cluster sum of squares, which is otherwise called as the inertia of a k-means algorithm. So when I am having only one single cluster, you could see that all the observations will go into the same cluster, right? All the algorithms will go into the same cluster. And we could also see that the sum of the squares of the error, which is nothing but the weight, the within the cluster sum of the squares is somewhere around 1503. Then what did we say? We will go to a 2 cluster solution, we'll go to a 3 cluster solution, and so on. We said we can go for different cluster solution. So you could see now different countries are a part of different clusters. Let's say I'm creating a 3 cluster solution. Everything else remain the same. So you will rename. You have created a column called clusters. So you will assign the labels to that cluster, and you will try to find out the inertia, which is the weighted, which is the within the cluster sum of squares. Finally, for the 3 cluster solution, you are seeing that the within the cluster sum of squares has come down, right? From 1500 for one cluster solution, it was around 1000 plus for 2 cluster solution. Now for 3 cluster solution, we are at 744. So you keep increasing the number of clusters. It might very well be possible that the overall can keep coming down. The overall WCSs can keep coming down. All right. So you could clearly see here, if I'm appending the clusters, the different clusters to each of the countries. So we could clearly see that Afghanistan and Angola They are belonging to the same cluster. When I'm going with a 3-cluster solution, right? Afghanistan and Angola, Albania and Algeria are a part of one cluster. Antigua and Barbuda became a part of another cluster. Probably on the other side, you could also see Yemen and Zambia. They are also similar to Afghanistan and Angola. Whereas the 3 other countries, Vietnam, Venezuela, Vanuatu, they are more or less similar to Albania and Algeria. So like this, if you keep on going ahead for printing, let's say, let's do one more thing, or probably we'll discuss it later. So you can try out 5 clusters, 10 clusters, 20 clusters kind of solutions as well, right? But the more important dimension here will talk about, right? What is the typical, how do I define each of these clusters? How do I define each of these clusters? Now, what is that we are saying? Okay, there are so many elements that are a part of cluster 0, so many elements that are a part of cluster 1, and so many observations that are a part of cluster 2. So what we are simply saying is, you take the, based on the cluster centers, right? You take the cluster centers for each of the column. So which means for 0, you take the cluster centers for all the elements that are belonging to that cluster. Similarly, for each of the columns, you try to find out the cluster center. Now, how do I interpret that cluster center? You could see here child mortality. When I took the average of people average of child mortalities of people who are a part of the cluster 0. Cluster 0 are typically the Venezuela, sorry, the Afghanistan, the Angola, the Yemen, the Zambia, etc. For them, it looked like the child mortality is positive. Now we have scaled the data, remember. So because we have scaled the data, generally the mean is at 0. So if I see some calculated value very higher than 0, then we may say that that particular cluster is very high on that particular variable. So in a way here, I could see that the child mortality is very high in cluster 0 countries. And you could see that the 3 clusters are well differentiated. Right? Probably this is more than 1, this is less than -1, and this is somewhere around 0. So possibly these are like somewhere in the middle. These are like the mortality is very high, and these are the countries where the mortality is very low. So we got a very clear-cut distinction on this particular variable, child mortality. Probably you could see the same here in terms of exports, right? This number is looking very low compared to the other 2. Probably this number is looking very high compared to this one. So we can say that exports are very low. So you can define the cluster 0 as those countries where child mortality is very high, the exports are very low, right? Health wise, right, not much of a difference between cluster 0 and cluster 1, somewhere in the middle. And similarly with imports also, not much of a distance with difference between cluster 0 and cluster 2. Yeah, the other important factor definitely is the income. You could see here, income is looking very widely different. Minus 1.23, plus 0.95 and plus 0.09. A clear-cut segregation. So income is one variable which is deciding the cluster. Now, if you look at inflation, it is not much deciding. So your zero and the second cluster have similar levels of inflation. Whereas at least the country one is having a very low, I mean, the countries which are in cluster one, they are low inflation associated countries. And if you look at the life expectancy, it is very clearly segregating again. Life expectancy is very, very low in the cluster 0, very high in cluster 1, and somewhere in the middle for cluster 2. So at least there are some variables which are playing a very crucial role. Same thing with total fertility. Cluster 0 has a very high fertility. Cluster 1 has a very low fertility, and cluster 2 has somewhere in the middle. And similarly with the GDP per capita something. So we can see that cluster 0 has a very low GDP. Cluster 1 has a very high, and cluster 2 almost. So most of the definitions for most of the variables, we are finding that cluster 0 is clearly differentiable from cluster 1 and then with the cluster 2. And because of this kind of a setup, we can say that there is a clear demarcation and a differentiation that is occurring across the various clusters. And after a few more, like if I go with a 4 cluster, 5 cluster, 10 cluster kind of solution, this explainability. So at least one cluster, each cluster should be having a very high value or a very low value, probably the highest or the lowest values, at least in one or two features. At least in one or two features, each of the clusters should have a very high value compared to the rest, or a very low value compared to the rest. So that is when you will get a lot of mileage in terms of explanation, or probably average in all, though it may not be a very high or very low in everything. It should be a kind of a average performance in all of them, somewhere in the middle in all the variables. So that could be one categorization, but definitely if you can get a very large value from the other groups or a very small value compared to the other groups, the clustering solution is coming out to be much appropriate. Right, the same thing in a different format. Probably I don't require this now. Okay. So we can very well find out for whatever is the number of clusters that we are finding out, we can very well find out the total distance within each of the clusters. So if I am going with a 3 cluster solution, I can very well look at what is the cluster 0, how many observations are there, and what is the within the cluster sum of squares. Cluster 1, cluster 2. So based on that, I can very well find out how many clusters are there, and what is the typical distance within each of the clusters. And one more thing I can also look at is, I can look at what is the level of correlation that is existing between all the variables that based on which I am taking a clustering. To a large extent, they should be, to a large extent, all these variables should be independent. Because if there is a kind of interdependence between different pairs of variables, it is quite obvious that one variable is influencing the other. So when I am taking the distance between two observations, right? So it would look like a double counting, because we have included one variable and we found the observation to be very close or very far off. But if I'm including another variable, which is again having a very high correlation with the first variable, it is highly likely that the distance between the two observations with respect to the second variable also will come out to be similar. So if it is a high distance in case of the first one, it might very well be a high distance in case of the second variable also. And when I'm trying to find out the total distance, obviously it will have a kind of an impact. And because of that reason, what we say is, if at all there is a very high correlation between the variables or among the variables, it's better to handle that high correlation between them by doing some kind of activities. We'll talk about the principal component analysis slightly later, but these are different ways of doing a kind of a dimension reduction. So some of the activities you have already looked at with respect to dimension reduction, right? We did that feature selection mechanisms. Right, especially we talked about a few feature selection mechanisms which do not require a target variable, right? For example, duplicate features, features with a large, very high correlation, but not a correlation of +1 or -1. So these kind of feature selection mechanisms you can try out, and you can eliminate some of the features. Or later on we will be seeing we can use mechanisms like principal component analysis to club some of the highly correlated features and thus reducing the dimension as well. So overall, if I look at the within the cluster, of course there are a few clusters or within there are a few variables which are highly correlated. I could see here life expectancy and child mortality. They have a -0.91 correlation. Child mortality and GDP is also having a very high negative correlation. So it looks like some of the variables are very highly correlated here, whether it is positive or negative, but they are very highly correlated. So in this kind of a solution, probably the principal component analysis works much better. You just right now understand that in this kind of a solution, the principal component analysis will work much better because we are seeing there is a very high levels of correlation. So in some cases you see here 0.97 correlation. Income versus GDP. It's a very high correlation. So there are some positively very high correlation, there are negatively very high correlation. So in this case, we may not want to talk about 9 or 10 variables here. I can very well restrict myself to 3 or 4 variables. We'll talk about it when we go to once we finish off this cluster, I will again take the same problem. We will relook at this problem after doing the principal component analysis. Okay. So this is what, but when I look at the cluster wise, so which are the determinants of the cluster? what you could see is the income is having a very high correlation. So income is playing. So with this correlation, you can very well talk about which variables are seriously impacting the cluster. So you can even do a kind of a sequencing also, prioritizing also, because we have standardized all the variables in the beginning. So whatever is the kind of correlation that is coming out, whichever is the variable that is carrying the highest amount of correlation, whether positive or negative, that would be the most important separator. So probably you could clearly see income, followed by total fertility, followed by GDP, and probably followed by child mortality. So these four are the top most important variables in doing the classification across the countries, clustering across the countries. Probably a variable like inflation is almost, or even the imports, they are very, very negligible. So which means their importance in terms of clustering the various countries, probably the imports is not playing an important role, or the inflation is not playing an important role, and so on. So this is just a plotting of the same importances. So the ones towards the left extreme and the ones towards the right extreme, those are the ones that are really, really important in terms of the clustering. So the clusters are clearly segregated based on the variables that the features that are lying on the either side, either of the extremes of this typical graph. Now, what should be the ideal number of clusters? What should be the ideal number of clusters? Now, for that, because we do not have an explicit way, right? We have to try out all combinations, and based on that, we'll have to come out with the best possible clustering number. So this is where what we say is, you take the range from 2 to 15, because here I want to go with the square root of the total number of observations. So my total number of observations was around 169, 170. So possibly I can very well go with the 13, or 13 should suffice, right? So I am taking from 2 to 13. I can start with 1 as well. But if it is 1, we already know what is the within the cluster sum of squares. So I would like to go with all combination. So we are starting off with the k-means algorithm, where the number of clusters is equal to the k, which is always taking a value between 2 and 15. And we are simply calculating the within the cluster sum of squares for all the k values, for all the cluster values. So you could clearly see here, we are plotting by taking 2 to 15 on the x-axis. Obviously, when you say 2 to 15, only 14 will be plotted, right? So when you are starting off with 2, you are going until 14 with increments of 1. So right from 2 to 14, we are looking at the inertia in each of the cases. So x value, on the x-axis, you are taking the number of clusters, and y-axis, you are talking about the WCSS. Now, based on that, what we could see is, this is the way it is falling. So initially, we saw that the WCSS was somewhere around 1000. Whereas when I go with a 14 cluster kind of a solution, I am seeing that the WCSS has come down to either 400 or even lesser than 400. Right? I could see that if I'm printing the maximum when it was 2 cluster, We saw that the WCSS is around 989, but when we move to a 14 cluster kind of a solution, we are seeing that the WCSS, which is the within cluster sum of squares, has come down to 351. Now, where do I put a kind of a knockout here? So for that, I'm trying to find out the percentage difference across. I'm trying to find out the percentage difference in each of the cases. So in the first case, the fall was by almost 32%. From 989, there was a fall up to 744. Right? And so that one has resulted in a fall of almost 32%. And after that, the fall was around 11%. The fall was around 7%, coming down, down, down. And after that, it has again started going up, which is like it got flattened. Right? Probably the fall was, so basically what has happened, you should see if the fall is increasing more and more, then it means the solution is becoming better and better. But if the fall is decreasing a lot, right, probably from 32% fall, probably in the next iteration, if there was a kind of a 40% fall, then you would see that it is going steeper. But if from a 32% fall, you see a 5% fall or a 10% fall, you are seeing that the graph is actually taking a kind of, you see here, you just try this scenario. Let's say we had 100 for a 2 cluster solution. 3 cluster solution, suddenly I saw this WCS has fallen to 70, which is like a big fall. Now suddenly in a 4 cluster solution, I see from 70 it has fallen to 65. Right? It has fallen by a very small amount. But rather than that, let's say from 70 it has fallen to 30. What you will find is you will find the data to be as steep as this, or probably you will find it to be more steeper. So as long as the fall is becoming more and more steeper, what we'll say is we'll continue. But the moment we see that the fall has become very much horizontal, that is what we call as an elbow method. The moment the fall becomes very horizontal, that is when we say we can stop with that kind of a solution. So here we could see that suddenly from 32% fall, it has gone to 11% fall. So we can very well say that the initial solution, which is a 2 cluster solution, that itself is a better solution, because when I came to 3, there was a fall. But when I went to 4, there was no fall. The fall was very, very marginal. So in some cases, so if the fall is very, very marginal, I don't need to move from a 3 cluster solution to a 4 cluster solution. But from a 2 cluster solution, I can very well move to a, so you could see here one more. Initially with a 1 cluster solution, we had 1500. And a 2 cluster solution, it has given a much more steeper. From 1500, it has come to 989. So it was a big fall. Right? So 1500 to 989, it was like a big fall. So compared to 989 to 744, the right the fall is not that heavy. So I can even stop at a two cluster solution because that was the time when the steepness was higher. But probably 32% was also not a bad kind of a steepness. So that's where either I can go for a two cluster solution or a three cluster solution, because after that the fall has almost stabilized. So we don't get too much of a benefit out of going for a slightly higher number of clusters for this problem. Similarly, now you can talk about the Silhouette score. I have already talked about it. It's a method of interpretation and validation of consistency within the clusters of data. So I can very well talk about how consistent, how closer are my clusters within and how farther are my clusters between. So it's a measure of how similar an object is to its own cluster. So that is what is called as cohesion. So within the cluster, how close are the various observations? That is what is called as cohesion compared to the other clusters. So between the clusters, how much separated they are. Both are important. Within the cluster, they should be very, very close to each other. Between the two clusters, they should be very, very far off from each other. Silhouette score ranges from -1 to +1. A very high value indicates that the object is well matched to its own cluster and poorly matched to the neighboring clusters, as we have already talked about A minus B by maximum of A comma B. So if the if B is 0, then only we can very well talk about the Silhouette score to be 1. Otherwise, it can go higher and higher, but it will never touch 1. So the maximum value is +1. If most objects have a high value, then the clustering configuration is very, very appropriate. So basically, if you are looking at majority of the observations or majority of the clusters, we could see that the distance is very close to 1. Then we can very well say that the clustering mechanism has been accomplished quite comfortably. Whereas if they have a very low or a negative value, then probably you can very well talk about within the cluster distance being very, very high, between the cluster distances being very much negligible. So the same thing, experimenting between 2 and 15. Let's say I want to take 2 to 15 number of clusters. I can very well find out the k-means. I can, for each of them, we are creating a k-means, we are predicting the values, but we are computing what is called as a Silhouette score. We have a direct function which will compute the Silhouette score. And we can typically do a plotting of a bar graph with the Silhouette score. Now you could see the maximum came for a two cluster solution only. Right? The maximum Silhouette score here has come out for a two cluster solution only. The three cluster solution is the next one which is closest to it. Probably 4 and 5 are closer, but after a point, probably we have seen that there is a decrease in the typical value. So the maximum, we should always look out for the maximum Silhouette score, because it's a difference between the between sum of squares and the within sum of squares. Obviously, we want this gap to be the highest possible. So you can very well consider the highest Silhouette score. So based on this, you can very well say that a two cluster solution is more appropriate. I don't know why it came out to be 6. Okay, let me just recorrect it. So for that, it's better that I run the data once again because there is a runtime that was expired. Right. So these things we have already computed. Even the Silhouette score has confirmed that a two cluster solution is much better compared to the other clusters. So probably we'll go with the two cluster solution itself. So when I'm going with a two clustered solution, you would clearly see, okay, we should fit the cluster labels. Okay, so we can very well fit these cluster labels, and you can very well do the various computations. Possibly we will do this computation directly. This is a better computation. We can very well look at this computation for our two cluster solution. So this is how we are getting the two clusters. You could clearly see the child mortality being a very good differentiator. Cluster 0, very high child mortality. Cluster 1, very low child mortality. So you can very well clearly interpret. Some of them are not that highly different. Income is very highly different. Right. Similarly, life insurance, life expectancy is very different. All right. Then we are also having a total fertility rate that is also very highly different. GDPP is very highly different. So we could see that some of the factors are very significantly different across the two clusters that we have formed. So depending on which, what is the appropriate number of clusters? Now, how many countries are coming into each of the clusters? Cluster 1 is there with 94 countries, whereas cluster 0 is there with 73 countries out of the 167. So you can very well say that probably the 73 countries that are there as a part of cluster 0, they are probably very underdeveloped kind of countries, right? So we can talk about, we can very well see which of those countries have clusters as 0. We can very well talk about which of those countries have clusters of 0, right? So we can very well talk about we can very well do a filtration with respect to which of the countries are having a 0 and which of the countries are typically having a 1, and based on that we can say we can classify the countries. So this is what uh, this is how you can very well come out with this is how we can very well come out with the typical clustering and trying to identify which we can yeah, so we can very well see which of them are falling into the cluster 0 and which of them are falling into the cluster 1, and based on that we can do the appropriate the next step. So but here we did not get a large number of clusters, whereas in some kind of problems the number of clusters could be pretty large. In that case we can very well get smaller groups, and when the groups are pretty much smaller you will get much more to analyze across the clusters. All right, so this is what is about the k-means clustering. If anyone has any kind of queries on the k-means clustering, we can do a kind of a discussion. All right, okay. So revision of the logic or math, it's a very simple math for us. Right, I'll take a two cluster solution. Let's say this is one cluster. These are the observations. So this will be my cluster center. There is one more data. Let's say these are my observations. Right, this is like two variables, x1 and x2. So if I look at their clusters, this is the cluster center or the centroid. So I can find out this is the within cluster sum of squares 1. I can find out the Euclidean distance between C and X, C and X, C and X. I can find out the Euclidean distance between the centers, which is WCSS1. Similarly, I'll get the WCSS2, right? So these two put together, and probably I'll take the kind of the average distance. So it's as good as saying the better way of positioning it is I take the distance between x, y, this and this, this and this, this and this. Rather than that, I take it as the distance between each observation and the centroid. So I can get the average distance here, I can get the average distance here, or I can get the total distances here, and after that I can do a simple averaging. So this is what will come out as my within cluster sum of squares total, or average within cluster sum of squares. Then similarly, one quick way is I take the distance between these two centroids. I take the distance between these two centroids, right? So that one will give me the between, so the average, because it's only one value, average between cluster sum of squares. If there is a third cluster, then probably we'll take the average of the three centers. So it's as good as saying you can find out the distance between each of the pairs of observations. So if I am having the observations 1, 2, 3 here, one way of talking about is I can very well find out the distance between 1 and 2, 1 and 3, 2 and 3. Then probably if they are like 4, 5, 6, 7, then between 4 and 5, 4 and 6, 4 and 7, 5 and 6, 5 and 7. So I find out all these pairs of distances and I find out the average distance. So that distance is what I am calling as the within cluster sum of squares. Rather than doing that, I can do the same thing, right? I can take each of the distances from the cluster centers, and probably I can simply add up those distances. And similarly, I can find out the distances between, and I would get one metric for between cluster sum of squares. So what we are saying is probably if I'm taking a between cluster sum of squares average and minus the within cluster sum of squares, and I divide it by the maximum of between cluster sum of squares and within cluster sum of squares. This is what we are calling as a Silhouette score, right? So obviously if you look at this, if I have one cluster, a very small cluster, right? Almost all the observations are very close to this cluster. I have another cluster here, with the observation somewhere here, right? You could very well see the distances, the average distances within the clusters is very low, whereas the average distance between the cluster is very high. So in that case, my BCSS minus WCSS would be WCSS will be a very small value. So this difference would be approximately equal to the BCSS only. And again, if I am talking about the divided by the maximum, so probably here it is the absolute values of BCSS and WCSS. So the maximum is always the BCSS here. So you will get this ratio to be very close to 1. And probably in the other way, right, in that case, what we are saying, probably this is one cluster, where this is the cluster center. Probably this is the second cluster I got, where this itself is the cluster center, right? So that is where the cluster centers of both of them are very, very close, which means we clearly see that the distance between the clusters is almost negligible. So So whatever are the distances, we are seeing that the distances, total distances within the clusters is very, very high. So in that case, we will end up typically with a value which is closer to -1. Does that help for us? Or you can have a follow-up question, no problem. Okay, otherwise I'll move a little bit. So in a simple nutshell, you can very well talk about some measure of how closer or how nearer or how similar one observation is with respect to its own cluster compared to the other cluster. So you can very well we talk about the average inter-cluster distance minus the average intra-cluster distance, and you divide it by the maximum value of either the inter-cluster distance or the intra-cluster distance. All right. Fair enough. I'll move on to the next approach as well. The next approach is hierarchical clustering. This is a slightly different mechanism. Though it uses distances only, even this mechanism also uses the distance between the observations only to do the clustering. So all that Euclidean and all that we have used, they come in handy here as well. So it is also called as hierarchical cluster analysis. Groups similar objects called clusters. So here, rather than we specifying how many clusters are required, right? It actually creates a kind of a tree. It actually creates a kind of a tree. We'll talk about it. That tree actually talks about which observations are closer. So it's a kind of a big picture. It actually creates something, a big picture, plotting all the observations in our data based on where they are with respect to the distances, right? So we'll talk about it. So that tree is otherwise called as a dendrogram. It's not a tree, but just it looks like a tree where the various branches are coming out. Some such kind of a flow is coming out. But otherwise, it is typically called as a dendrogram. So we'll talk about it just in a while from now. So in case of hierarchical clustering, where we are talking about agglomerative and divisive. What does this mean? Agglomerative. So initially what we say is if I have 167 observations, 167 observations are there. We will start with 167 clusters. Right? Each observation, one observation, one cluster. So we have 167 countries. Each country will be a different cluster to start with. Right? And then Depending on their distances, we keep merging the clusters. We keep merging the clusters until we form one single cluster. So we start with 167 clusters. We keep merging all the clusters one by one until we finish off all the clusters, merging all the clusters, and finally create one master cluster. So that is what is called as agglomerative. It is otherwise called as a bottom-up clustering approach. We start with 167 separate clusters. We integrate all of them into one single cluster. But we'll talk about what do I do if I want 2 clusters, 3 clusters, 5 clusters, 10 clusters, etc. But that is the approach that is built. And in case of divisive clustering, which is otherwise called as top-down cluster, we start with one single cluster containing all 167 observations. And then we keep on splitting that cluster until we arrive at 167 clusters. So we start with 1, go to 167 in a divisive clustering, whereas we start with 167 clusters, go to 1 cluster in an agglomerative clustering. Right? In both the cases, we will be creating a dendrogram. It's a visual representation of the compound correlation data. Right? It looks like a tree. We'll just see in a while from now. Probably if you look at it, this is what we call as a dendrogram. We'll discuss about it. Right? So, yeah, it's a representation of the compound correlation data. So the individual compounds, here compounds are nothing but clusters, are arranged along the bottom of the dendrogram. So you could see here, all our 167 observations, they are arranged here at the bottom of the dendrogram. All the 167 observations are arranged at the bottom, and they are typically called as leaf nodes. So you could see, just that's the reason I referred to them as tree. You could see that the bottom part, all of them are looking like leaves. Compound clusters are formed by joining the individual compounds or existing compound clusters with the join point. Okay, so it can very well happen that initially you will have something like this, right? So this could be my observation 40. This could be, I'm just taking, this could be my observation 70. These two could be joined like this. And then I could have my observation 23 and my observation 66. These two could be joined together like this. So like this, depending on the distances, all the joinings will happen. And after some time, it can very well be possible that these two clusters, they can be joined again. Then these two clusters can be joined with some other point, these 3 clusters. So like that, this kind of a joinings can very well happen. Some such kind of joinings also can happen. Right, we'll discuss on how that joining is happening. But the dendrogram will typically be created in this manner. All the individual observations, they will be clubbed, and such a kind of a tree format is typically created. And this format is typically called as your dendrogram. So here also, we can use the same Silhouette score mechanism to really see which clusters are close to each other and which clusters. So what is the how many clusters solution is an appropriate solution. Here also you can talk about the same thing. Because I'll tell you how you split. If I want, let's say 3 clusters, 4 clusters, 5 clusters, how do you typically do the splitting part? But the evaluation of the cluster goodness can very well be done based on the same method that we have used in the k-means also. Even in the next method that we are going to deploy also, we would be using the same fill out score. So either you can use the weighted, the within the cluster, whenever I see the word W, somehow I don't know, weighted is a word that comes immediately to my mind. So that's where I was making the common mistake every time. So it is the within the cluster sum of the squares, which is otherwise called as an inertia approach. Or the second approach is always a more robust approach, which is called as the fill out score approach. So for a little bit of more clarity on the dendrogram, it's a diagram that shows the hierarchical relationship between the various observations. And in a way, it's a summary of the distance matrix. Now, as I told you, right, so here if you are seeing this, actually speaking, this is an axis. This is where the distance is. So it might be possible that the 40th observation and the 70th observation, they are having the smallest distance between them. And that is the reason initially they both are joined. Right? And once they both are joined, you just observe one more thing here. Once they both are joined, there is now the next, let's say 23 and 66. The distance between them is somewhere here. Right? Now, there will be, let's say now, here we have 40, here we have 23. Let's say now the next smallest distance is between 40 and 23. But 40 is already a part of one cluster, one combined cluster. 23 is a part of another combined cluster. Right? So what we generally say is, now 40 and 70 are typically combined. And 23 and 66 are typically combined. Now, if I have to join these two clusters, different algorithms come into picture. Right? Different algorithms will come into picture. What are those different? So whenever I want to combine one cluster is a compound cluster I am referring to. Whenever I want to combine one compound cluster with another simple cluster or another compound cluster, we will start using the linkage methods. We'll start using the various linkage methods. Right? So there is one linkage method which talks about the smallest distance between the clusters. Right? So basically, let's say 40 and 23 are having the smallest distance, then probably that is the distance that would be used to join these two clusters. Or sometimes we'll go for the largest distance. So whichever is the maximum distance between these two, let's say 70 and 66, they are having the largest possible distance. So these two clusters will be combined at that level of distance. So the largest distance is somewhere here. These two clusters will be joined somewhere here. Or sometimes it could be the average distance. So we can talk about the distances, the four distances will come out here. So whatever is the average distance between these four, at that level, these two clusters will be joined. And in some cases, there is a kind of a Euclidean distance. So we have different such kind of distance mechanism. There is a Watt's distance. So there are different kinds of joining mechanisms or the linkage mechanisms. Right? A common dendrogram. So it's a summary of the distance matrix. Dendrogram suggests that C and D are much closer to each other than C and B. So C and B are combined at a lowest height, and probably the B would be joining them at a later point. Dendrograms cannot tell you how many clusters you should have. So dendrogram will create a kind of a combined picture like this, but it will not tell you how many clusters you want. I'll tell you there is a simpler mechanism to create clusters from the dendrogram. But dendrogram as such does not talk anything about the number of clusters. Right? So the incorrect interpretation is that dendrogram shows that there are two clusters as the distance between the clusters are highest between 2 and 3 clusters. So that is when you are using a dendrogram. So probably this is the distances, right? You can very well say, sometimes that's what people do. Okay, the gap is much higher here, the bit, because this is the height. So what people generally say is here, the height is much higher compared to all the other heights. So which means these two sets they are integrated at a much bigger height, which means probably it's better to have two clusters. That is what is a typical interpretation people talk of, which is not the typical interpretation that we should think of. At the end of the day, you can very well create any number of clusters from the dendrogram. And as I have told you, use the Silhouette score as a kind of a differentiator. Don't try to look at what is the distance, where the distance is maximum, and don't say that that is the number of clusters. That is where somewhere I saw that people make a very typical wrong interpretation. So, okay, so in general, it's a mistake to use dendrogram as a tool for determining the number of clusters. You cannot use a dendrogram to determine the number of clusters in the data. So it's always better that you use the Silhouette score to determine number of clusters that are present in the data. Now, how do I create that dendrogram? Right? So we have in the SciPy, which is the scientific Python library, we have a module called cluster. So we have we can use different kinds of clustering algorithms there. So the hierarchical clustering is a part of that module. The reason why I have chosen that is that has a very important function called plotting a dendrogram. Right? Now, all we have to say is while plotting the dendrogram, initially there is no problem. Initially, the two individual observations are there, so I can find out the distance between the observations and I can very well start with the smallest values. The problem comes when one observation is already there as a part of the cluster. As I have already told you, the 40th and the 70th observations are already integrated into one cluster. Then if I have to look at their relationships with any other individual observation or with any other cluster, then we have to look at the various methods, linkage methods that are there. Right? you can very well see that there are a good number of linkage methods. So you could see here, the linkage method could be single, and you could clearly see the explanation for the same. So single is the nearest point algorithm. Nearest point is nothing but the smallest distance. So when one cluster is looking at joining with another individual or another cluster, we look at the nearest distance. Even if one observation in that cluster has the nearest distance with the second observation or third observation, then they are joined. Then similarly, we can use the other. So there is something called complete. Complete means it goes for the farthest point, which is the maximum most distant. And similarly, if we talk about average, it talks about the average distance. So you could see here, you can find out the modulus of u and modulus of v, which is like the distances for each of the pairs of points, and you can find out the average. Then you can also find out the weighted average kind of thing, giving a weightage based on the distances of each of the points. Then you can very well take the centroid, right? So this is also one more mechanism. Or you can very well take the median distance. Instead of the average distance, you can take the median distance. And you can also talk about the wards distance. So these are the different distance computing mechanisms, especially between a cluster of a compound cluster and one or more individual or compound clusters per se. So this is one thing that would be the differentiator. The method, right? Probably depending on the method that you are giving. Let's say if I give a single method, you look at the axis out here. If I am taking a single method, my axis has gone only up to 3.5 or something, right? And you could see that probably the shape of the cluster dendrogram was completely different. And if I go with a complete method, which is the farthest distance, you will find the distances to be much higher. You see here, the solution is slightly different. And if I go with the ward distance, which is more and more based on the Euclidean distance approach. So this is what is a kind of a solution. So probably we are getting different solutions and probably the different clusters also when we are changing the method. And even we can change the distance mechanism metric. So you by default, it's a Euclidean metric that is considered, but you can very well change those metrics also. There are a good number of metrics that are supported here as well, right? So you should look at the metric. So there are different metrics that are supported. You can very well use the most common kind of metrics as such. Okay. So you can very well do this. Depend now you can very well. So how the clustering happens? Probably you look at here. It's just a horizontal cut that you make. So if you put a cut at 30 horizontal cut, there are two dangling wires that are coming up. So those two will be your two clusters. Or let's say if you put a cut at 20, 1, 2, 3 danglings are there. So which means you can create a 3 cluster solution. Or let's say you put a cut at 12 or something. 1, 2, 3. Still it's a 3 cluster solution. But let's say you put a cut at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 cluster solution can come up. So depending on how many clusters you are interested in, the cut can be put at that appropriate height. Right? Let's say here you want a 6 cluster solution. Right? I'm just, you can try out, because once you get something, you can create fill out score and all those things. So let's say I want to go with a 6 cluster solution by using Euclidean distance, and I'm using a Watt's distance mechanism. So you can very well see that I'm able to create the 6 cluster kind of a solution. And you can very well look at different, so there are the countries wise. Now you can say which country is going to which. Probably let us see. We'll try to print X. You could see here Afghanistan is with a cluster 0. Albania and Algeria are with cluster 1. Probably if I look at the top, or otherwise we'll have to print all, but let us see. So you could clearly see here Afghanistan, probably Bangladesh, Benin, Burkina Faso, Burundi, Cameroon, they are all a part of one cluster. Right? We could see Bahrain. Right now, only Bahrain is a part of one single cluster. Canada, Bulgaria, Bosnia, Barbados, Bahamas, Austria, Australia, they are all a part of one cluster. Antigua and Barbuda and so on. So like that you can see that there are different countries that are coming as a part of this 6 cluster solution. Even if I look at the tail, okay, along with the Bahamas, I am getting UAE with Bahamas, right, in the cluster number 4. So we are seeing that different countries are constituting different clusters. And you can very well look at what is the differentiator across the cluster. So sometimes you may not find anything interesting. You look at here, in cluster 0, probably cluster 0 and cluster 2. These are the two which are very high on child mortality. And cluster 3 and cluster 5, both of them are very low on mortality, right? And even cluster 4 is also moderately lower. You may have to give some such kind of words, right? Cluster 1 is more or less average on the mortality. Whereas if I look at in terms of exports, possibly cluster 5 is very high on exports, followed by cluster 4. And cluster 0 is very low on exports. All other 3 are more or less very quite similar. So you may have to give some such kind of explanations in case you want to differentiate what are the characteristics of each of the clusters. But you can also perform a kind of a Silhout score You can try it with many number of clusters. For each solution, you can go with the Silhouette score. And based on that, you can still evaluate what is the optimal number of clusters that you can have. So this is the straightforward mechanism called hierarchical clustering. Right, you can very well decide on the number of clusters, and you can very well use the Silhouette score to talk about which what is the best possible cluster solution for us. So we will move on to the third mechanism, possibly in our next class. With that, we'll complete the clustering, then we'll enter into our we'll talk about the principal component analysis, which is another unsupervised learning algorithm. So we'll do these two algorithms in our next class. DB scan can actually help us in even identifying the outliers also in the data. So we'll try to use the DB scan, which is a density based clustering algorithm, to do the outlier analysis as well as for doing the clustering as well. All right. So I'll have to rush to some other meeting, as I told you in the beginning itself. So if you have queries, I'll address them separately. Yeah, I'll share the modules. I think I missed out on that. So if you are having queries, I suggest that you can post them there. I don't see any kind of disadvantage of the Silhouette score. At least I did not. I cannot visualize it because it's a simple thing that is talking about the distances, which is for any clustering algorithm it requires. I possibly the extremes is something we may have to think through. If there is any disadvantage, probably we can Google it out. But immediately it's not coming to my mind, because generally I would prefer it a lot. I have used it in a couple of practical algorithms as well, in a practical problems as well. But yeah, let me Google it out. Right, immediately it's not striking me. You can also do that. All right. Thanks a lot. I'll again come back on Saturday. We'll have slightly more detailed discussion on that day. I have to rush to another meeting. Thank you very much. Take care. Bye bye.